Welcome to part 4 of our series on the PETS algorithm. In this video, I'm going to be building out the actual model that we are going to be training. And we might get into a little bit of the ensemble piece. Let's see how far we go. So we're going to call this model.py. We're going to be very creative. And we're going to need a few of the standard imports. So we'll need to import OS. We'll need to import torch. We'll need to import torch.nn as nn. And we'll do torch.nn.functional as f. And then our actual model is going to be really simple. We're going to take we're going to say class dynamics model, and we'll base that off of nn.module. And we're calling it the dynamics module because we are modeling the dynamics of the environment. So we'll do our init, and we can get rid of this and just do hidden dim is equal to 256. We'll default to that. OBS shape will be none, and action shape will also be none. Okay. And we will do super dynamics model and self. And then we do not need to pass anything into our init method. We just need to call it. All right. So we're going to have self.fc1, our first fully connected layer. We're not taking in any images, so we don't need to do any, any CNNs. We're just going to do our fully connected layer as our first one, and that'll be nn.linear. And it's going to be the observation shape plus the action shape, because again, if we go back to our design, we're taking in an observation and an action, and we are going to output what we think the next observation should be, or specifically the observation diff and the reward. So our input, obs shape plus action shape. We'll do hidden dim. For our second fully connected layer, we'll do nn.linear, hidden dim, hidden dim. I guess we could have called that last one input, but oh well. And then we'll do self.obs diff output, nn.linear. And that's going to be hidden dim by obs shape. So this is going to be outputting the change or the predicted change from one observation to the next. So we've got obs diff output, and then we're also going to have reward output. So self.reward output equals nn.linear, and that's going to be hidden dim and 1. So again, we are trying to output the expected reward along with the change in the environment state. So let's go ahead and do our forward method. So def forward, and this is going to be self, state, action. We'll do x equals torch.cat, state, action, and we'll do dim equals -1. And we're going to do x equals f.relu and self.fc1. And then just copy and paste that and do fc2. And then we will grab the obs diff and say self.obs diff output x, and reward is going to be self.reward output and pass in x. All right, cool. So we have our model. Again, really simple model, nothing overly complex there. Let's go ahead, and we're actually not going to use it yet. I'm just looking over the code. There's really no place that we're going to reference the model directly. We're going to reference it purely as an ensemble. So again, ensemble is what's in the name, but all that really means is that we're going to batch a bunch of models together. And in batching those models together, we're going to get something that we, in the code, can interact with as if it's a single model, but it's going to have a lot less overall. It's going to be much more accurate because we're going to have many models making predictions about the environment. So that is part of the power of this algorithm. So no real way to test this directly without writing a bunch of code that's not going to make it into the final solution. I will say, if you were coding this from scratch, you would find a way to test it directly. I did in the first iteration, but since we're coding this all out at once, it is not really necessary. So this section is going to get a little bit complicated. So work with, or let's just hack through it. So we're going to say ensemble model. Okay. And we're going to do our initialization. And the params we're taking in are num models, which will default to 5. Hidden dim, which will again default to 256. Obs shape is still none. Action shape is still none. We'll fall down to the next line. Device is equal to none. And learning rate is equal to 0.0001. And then we can get rid of that final none on the return. That's not necessary. We're going to have a list of models. So we're going to use a list comprehension to build our list of models. So we're going to say self.models is equal to dynamics model. And then we're going to pass in hidden dim is equal to hidden dim. Obs shape is equal to obs shape. Action, actually let's fall down to the next line. That'll just make this easier to read. Action shape is equal to action shape. And that should be all. And then we're going to say to device for underscore in range num models. And we'll just drop that down as well. Actually, that might cause problems. We're going to leave that in. Okay. All right. So what that's basically going to do is loop through for, the range in num models, which we're defaulting to 5. It's going to return a list of models in self.models. We're going to need to do the same thing for self.optimizers. So self.optimizers is equal to torch.optim.atom m.parameters LR equals learning rate for m in self.models. So again, in this case, we already have our models. We're just looping through all the models, and for each one, we are going to pair it with an optimizer. And then we'll go ahead and say self.model save dir is equal to models. Okay, that's our init method. A little weird, but it will work. Now we need to code up a train step. So this is basically because we're using these models as a batch, we want to be able to train them. We're basically building an interface so that we can treat this kind of like it's not multiple models when we're using it in our training. So we're going to say def train step self states actions next states rewards, and we're going to capture total loss, which is currently 0. And then we're going to say for I, and then in parentheses, model optimizer in enumerate zip self.models self.optimizers. So here, what we're basically doing is trying to loop through our entire list of models and optimizers for a train step. We're going to grab a slightly different batch per model. So that is a design decision. We could have gone either way. We could have trained all models on the same batch of experiences. We are going to try to train different, samples on different ones here. So indices is equal to torch.randint 0 length of states. And then this is going to look a little funny, but parentheses length of states. There we go. Those are our indices. And then we're going to grab batch states equals states indices. Oh, I spelled that wrong in one place. Okay. And then batch next states is equal to next states indices. And batch actions is equal to actions indices. And batch rewards is equal to rewards and our indices, which I keep spelling incorrectly. All right. We are now going to grab the diffs for the observations. So we're going to say obs diffs is equal to batch next states minus batch states. So again, we're trying to get the model to be able to predict what the change in the state will be given an action. So if I take a step forward, what is the difference in the environment? So this is grabbing the real difference in the environment, and then we're going to train against that. So we're going to say predicted obs diffs predicted rewards equals model batch states batch actions. So we're feeding in the actions that were taken in the states, and we're trying to predict the differences and the rewards. Again, we're just modeling the environment. We're trying to make the models tell us what the environment's going to look like. Our loss is going to be f.mse loss. And we're going to have a couple of torch cat statements here. So we're going to say torch.cat, and that's going to be predicted obs diffs. Predicted, let's see, predicted rewards. And we are going to zip those along the dimension -1. So put a comma after that paren, and then we're going to drop down and do another torch.cat. This time for obs diffs and batch rewards. And we will again concatenate those along dimension -1. And I lost a paren there, so we're going to add that one back. All right. Now finally, we get into something that should look pretty similar. We're going to say optimizer.zeroGrad, loss.backwards, optimizer.step, and then we're just going to add to total loss. All right. And then after our loop, we're going to come down here and we're going to return total loss divided by the length of self.models. So we're basically going to say that we want an average loss here is what we want returned. We don't actually really want the total loss. Because, obviously if you have many models, your loss is going to look like it's going up, and that is not the metric that I want to see here. So let's go ahead and work on our predict method and then some basics to save and load the model. So this is our training step. At this point, we can plug this into our training loop, but we also need an actual predict in here. So def predict self states actions, and we're going to say with torch.nograd, we're going to grab obs diffs, grab a blank there, rewards. Did not actually mean to add space there. That was unintentional. And then we're going to say for model in self.models, and we're going to grab obs diff reward is equal to model and states actions, and then we'll say obs diffs dot append obs diff and rewards dot append reward. Okay. We're going to return then an averaged prediction. So we're going to say obs diffs is equal to obs diffs dot stack obs diffs. And we're going to say rewards is equal to torch dot stack rewards. And then we can say obs uncertainty is equal to obs diffs dot var 0. Reward uncertainty is equal to rewards.var 0. And then finally, we're just going to grab the mean of those obs diffs. So the average avg obs diff is equal to obs diffs dot mean 0, and average reward is going to be rewards dot mean. Return avg obs diff avg reward obs uncertainty reward uncertainty. All right, so that was a whole bunch of code, but if we think about what we really just did, all we did is we tied a bunch of models together. We built a very basic model that's going to predict a couple of things. We tied a bunch of models together, so when we run a training step, we're going to train them all. And then we tied a bunch of models together so that we are returning an average of all of their outputs instead of, returning the standard single model for our prediction. Finally, and I wish I could say we were done with this class, we're close. We need to do some housekeeping methods to save and load the models. So we're just going to say def save the model. Self file name is going to default to latest. And we'll say os.makeDirs self.modelSaveDir. And we'll say exist OK is true. So hey, go ahead and make the directory. If it already exists, that's fine. Don't error. For I model in enumerate self.models torch.save model.state dict f for an f string, and then we're just going to say self.modelSaveDir / file name _ I .pt. Okay, and what that's going to do is save them under file name, so latest _1, latest _2, latest _3, and so on. When we go and do the same thing for load the model. We're going to say def load the model, self, file name equals latest. And in load the model, we are going to have for I model in enumerate self.models file path is equal to F and self.model savedr, just like we did before, slash file name. Oh, nope, I needed my curly braces there. File name underscore I dot pt. And then we're going to try a model load. And the reason we're doing a try except here is the first time it runs, it's not going to have models. And if you need to clear them out at some point, this might need to run and this part will fail, which is okay. So we're going to say load state dict and torch.load file path. And then we'll say print f loaded waits from file path. And then our accept file not found error. So the reason we're specifically accepting file not found error is if anything else happens, if it's anything but the file's not there, then we should still get an error that tells us where to go look. So accept file not found error, print no waits file found at file path. All right, that was a whole bunch of code, but we are done, except for this block that definitely looks wrong. Okay, that looks good now. So our model class is finally complete. We can come over here to agent.py and we can say from model import star. All right, and we're just going to go ahead and run this just to make sure that nothing in the actual import fails, and it did not, which is a good sign. So now we can go ahead and start to integrate this with our agent. And we're going to do a very basic part of this, and we'll pick it up in the next video. But for now, we will say self.model is equal to ensemble model. And obs shape is going to be obs.shape 0. Action shape will be action.shape 0. And device will be self.device. All right, we are now loading our model. Let's go ahead and run it one more time now that some of the actual code is loading and it still didn't error. Cool. We're getting there. Down in our train method. So previously we had stored transitions. Now we need to actually add a block that is going to do some training. Now, in most algorithms, you would add a training run every step. In pets, the recommended method is actually to break outside of this and to run a block of these every so many episodes. So it's a little bit different than what you might normally see. So what we're going to do is we're going to come down here up under this, episode finished printout. Actually, I don't even think we did an episode finished printout. That's fine. Let's see. So episode reward, if done or truncated break. Cool. We can get rid of print men size. So under here, we want to come in a couple of steps. And I'm slowing down because I want to make sure that we do this part right or this could end up being a little bit weird. Okay, so we want to be inside of the episode for loop, but not inside of the while not done. And inside here, what we want to do is we want to say if episode modulo 10 is 0. So every 10 episodes is what we're doing. Then for underscore in range 100, we want to say if self.memory.canSample batch size equal to self.batch size, what we said earlier. Then we want to grab our states, actions, rewards, next states, and it's very hard to type what you're not saying, which is why you'll see me putting the word and in sometimes. But we're going to add all of that and say is equal to self.memory.sample buffer, batch size equals batch size. Okay, and self.batch size. Okay, we're going to unsqueeze rewards and dones. So rewards equals rewards dot unsqueeze 1, and dones will be equal to dones dot unsqueeze 1 dot float. And then our loss will be self equal to self.model.trainStep states equal states. Next states is equal to next states. Actions will be equal to actions. And rewards will be equal to rewards. Okay. And then we're going to do I don't think we actually declared a writer up here, a summary writer. Let's see if we did. All right, we did not. I left that off because it wasn't necessary at the time. But now we're finally at a point where we need some metrics. So we're going to create a summary writer for TensorBoard. So we'll say summary writer name is equal to runs slash datetime dot now dot strftime. And then in here, we're going to do %y, %m, %d. We're just doing some date formatting. And we want capital H dash %m dash %s. All right, we have our summary writer name. We're going to say writer equals summary writer, summary writer name. All right, and I'm realizing that I didn't even include this because I wasn't thinking about it earlier. So up here, we need to do that one. Okay. Actually, let me go back up. I flashed through that really quickly. From torch.utils.tensorboard, import summary writer. I had it commented out. You need that import, or this isn't going to work. All right, so we now have our writer, which is declared right up here at the top of train. And then down here, under our loss, we will just say something like, hang on a moment. Writer.addScalar. Loss slash model. Loss and total steps. Not ordering, total steps. Okay. And let me make sure, I think we also left off total, no, we did include total steps, cool. Let's see if we actually incremented it anywhere, because I don't believe we have yet. All right, we haven't, so let's increment it right here. Okay. So what this should start to give us is it should start to give us some loss metrics as the agent trains. Now, we're not using the model for anything useful right now. We're still pulling from action space sample, but we should be at a point where it can start to learn things about the environment as we go. And this is probably also a good point to not be sitting here watching the environment run. Let's go ahead and change. Let's see. I think it was over here in train. Yep, here we go. Instead of render mode human, we're going to do RGB underscore array. And we are going to change this to 200 episodes. Oh, hang on. Cannot unpack non-iterable none type objects. Okay, so we have our first bug, which is fine. We will go fix it. All right, so predicted obs diffs, and we are passing in batch states, batch actions. Okay, here's a problem. It would really help if we actually returned anything from our forward method. If you were watching this earlier, you were probably yelling at the screen if you saw my problem there. All right, let's try this again. So something that we probably should have done is added some kind of, okay, so it happened in 17 seconds. We should probably add some output here. So completed episode, print, something like completed episode, with score, let's do episode reward. That feels like the right thing to track there. That at least gives us a little bit of output. And output is good when these things can be very, very slow. So you'll notice that every 10, it slows down and does some training, which is what we would expect. And if we do TensorBoard here, there should be a logdir called runs. And I'm going to pull this over here. So by just including that writer line, what we got is we actually got a graph of, and it's going to reset for each run. But what you can see here is our model, our ensemble of models is learning. It's learning the environment. It's learning to predict actions or the next states and rewards more accurately over time, which is exactly what we want to see. We want to see this line trending down, and then later on, when we're tracking scores, we want to see the scores line trending up. So I think this is a great place to go ahead and stop the video. In the, as usual, there will be a GitHub link with the completed code for this section. There will be a section 4 link down in the video description. If you need that, as usual, you should try to fix any problems you find yourself. You're going to learn a lot more from the project if you take the time to troubleshoot through those, but if you need it, the code's out there. If you're enjoying the series so far, do me a favor, hit subscribe. It helps. With that, I'm going to say I'll see you in the next video where we will be starting to put together the actual planning process that'll take all of what these models have learned and use it to make better decisions in the environment. So see you in the next video.